Thank you for attending this seminar. I was saying that fortunately my French is not that good at all, so I will do the presentation in English. Well, my name is Luis Guijarro. I am visiting links for the month of July. I come from the Technical University of Valencia, and Dario asked me to prepare a presentation for for what he said to me that it was the weekly seminar or so here in Links. So I will be very much pleased to give you a seminar with this title, because actually my research topic is telecommunication economics. My background is telecommunication engineering. I did my PhD in telecommunication engineering in computer networks performance evaluation, but for the last 10 years, I to some extent switched my research topic to telecommunication economics. I do economic modeling together with my colleagues, which are more focused on performance evaluation in mobile networks. So our current topic in the research group I belong to back in Valencia is wireless sensor networks. So from my point of view, from my research topic, I've been doing for the last 2-3 years economic modeling of services within these kind of networks. So I will be talking you today about a couple of economic models that I've been working on in the last years, with the aim of showing you which kind of models can be used, which kind of results can we can obtain within a scenario familiar to the computer science and the telecommunication engineering. Basically, the seminar is structured in 2 parts. Each one dealing with, say, a broad class of business models. One is called intermediation. Okay, so there is not at all. Yeah. There is one called intermediation type business model, and the other, which is more interesting to say something, is called platform type business model. Okay, so the first business model, the intermediation type, is, quite easy to understand, because the context will be the following. Say that we have one sensor or a group of sensors, say wireless sensor networks. I must say that I will be applying the economic models I will be presenting to the wireless sensor network scenario, but most ideas can be translated to other technology scenario or to other network scenarios. Here we have a sensor or a group of sensors that can sense data and deliver this to somebody. And we have users, customers that may wish to access this data. Okay, of course, without having to interface to every one of the sensor networks. So there is room for an intermediary. An intermediary which, in the simplest case, will be just intermediating in the delivery of data from the networks to the users. But what is more interesting to me is that this intermediary can use the data from the different networks in order to compose a service and deliver that service to the users. Of course, the quality of that service provided to the users will depend on the amount of resources, on the amount of sensing data, on the amount of the sensing data rate that the intermediary can gather from the networks. But basically, the rationale of an intermediary is what I have just said. So the objective of the economic modeling in one scenario as this one will be to check whether this business model is feasible. That is, if an intermediary may get positive profits. Okay, and of course, which is the best strategy, which is the best pricing strategy for the intermediary in order to maximize profits or at least to get reasonable positive profits. Okay, well, let's go to see which sort of models are used for each one of the agents that we have here in this model. That is the users, the intermediary, and the networks. Okay, as far as the users are concerned, I'm here presenting a couple of common models. The first one, which is related to the hoteling model, is the following. This U is a utility, which is a measure of the satisfaction of the users when receiving a service. Okay, we propose an expression such as this one for the utility of a user, where this V will be the intrinsic utility for accessing the service. This phi function will be, well, a non-decreasing positive concave function, which in this simple model depends on capital R. Capital R might be the total amount of sensing data rate that the service provider can use for delivering the service. So this phi of R would mean that the more sensing data the service provider is using, the more satisfied the user will be, or not just the amount, but the sensing rate that is used for delivering the service. Okay, and of course, if we assume that the users will pay a service fee for the service, this P will be subtracting here. Okay, this XU will be a part of the model with the aim of modeling, say, the unobserved part. Okay. This is borrowed from the original hoteling model. Well, this was a transportation cost from the user up to the point where the service is provided. But in a general sense, this can be used for modeling the unobserved part of the utility that the user receives. Okay, with this utility function, which I said it should be interpreted as a measure of the satisfaction. Tell me.
Is T time or something?
Oh yeah, this is a scalar, T times, yeah. From this expression, which measures the satisfaction of the utility, we could compute the demand of the service. To say it in a few words, the demand will be how many users will end up subscribing the service. Okay, for this we may model this XU as sample of a random variable, of a uniformly distributed random variable, so that given a total number of users, capital M, the number of subscribers, M, can be computed as capital M times the probability that the utility is greater than or equal to 0, which translates into this, and we can express it using this C function, which in the end is the cumulative distribution function of a uniformly distributed variable between 0 and 1. Okay. An alternative model for the user might be this logic model. In a logic model, the utility of a user has say an observed part, an objective part, and an unobserved part. When this unobserved part is modeled as a Gumbel distribution, okay, the model is called logic model. Okay, for the specific purpose of this economic model, the objective part of the utility received by the user is expressed as the logarithm of the ratio between the sensing data rate used by the service provider over the price charged by the provider. This I means that this expression of the utility can be used for the utility received by a user U from one or more service providers. Okay. While in the previous model, it is usual to set utility equal to 0 for the no provider option, okay, we usually have more flexibility with this kind of model, since we can associate to the no provider option, that is no subscription to any service provider, to a specific ratio R0 over P0. The point here is that if we proceed as we did before, given a total number of users, capital M, the number of subscribers to service provider E can be computed as capital M times the probability that the utility that a user gets from service provider E is the greatest of the capital K service provider. And this can be computed, and it ends up having this expression of the exponential of the objective part over the sum of the exponential of the different objective parts for the different service providers. Okay, this alpha, which is equal to mu over mu, is the ratio between this mu, which can be here as well, and the Gumbel parameter. The interesting thing here is that even being a parameter, this can be interpreted as the user sensitivity to the objective part of the utility that a user gets from a service provider. It is indeed a user sensitivity because you can check that if alpha goes to 0, all users will be distributed into equal parts between the different service providers. Whereas if alpha goes to infinity, then the service provider which offers the greatest ratio will get all the users, and no users will subscribe to the other service provider. So it is indeed a sensitivity. Okay, this will be important for the discussion of the results later on. If we consider the utility of the networks, we can have this model. We have different networks. Each one of the networks receives a payment from the intermediary, and each network pays a network access provider for accessing the network and delivering the data the service provider is requiring. Okay, so the utility in these cases are equal to the profits made by the agent, in this case each one of the sensor networks. Okay, these are is the sensing data rate that each network can provide. Okay, if we model this R as a random variable uniformly distributed between 0 and a maximum value, we can compute the number of networks that will connect, that will supply sensing data to the intermediary as the total number, capital N, times the probability that this profit is greater than or equal to 0, which end up having this expression. Of course, this is only one part of the supply, of the sensing data supply. The other part will be given by the mean sensing data rate provided by each one of the networks that can be computed as it is shown here, and this gets these expressions. The important thing is that this R times the N showing before gives us the total aggregated supply. That is, for a price A, for a unit price A, which will be the total sensing data rate that the service provider can get. Okay. So for a given A, this gives a subset of networks that, depending on its respective sensing data rate, gets positive profits. So they choose to deliver the data. And the expression of the total rate that the service provider can get, depending on the price A, is given by this. This is an expression for a supply. Given a price, a total amount of product can be computed. We can instead, and will be more useful later on, to derive the inverse supply. That is, A as a function of RT. And this will give us this expression. The interpretation of an inverse supply function is the following. If the service provider wants to get RT, total amount of sensing data rate for the service, this unit price A should be paid. Okay, so that's the meaning of an inverse supply function. Okay, that means that all this disaggregated model can be compressed and substituted and replaced by this aggregated model. Okay, where only those sensor networks that connect to the service provider are present, and where the total payment is given by RT times the inverse supply function. Okay. Okay, so far these are the second agent, and if we model the third agent, which is the service provider, the intermediary, this might be a sensible setup. This intermediary will charge a price P to any one of the users that decide to subscribe, and will pay this total amount to the N sensor networks that decide to connect and deliver the data. That means that the utility of the service provider, the profit, will be given by the revenues that the SP gets from the user minus the costs incurred in paying the sensor network for the data. Okay, assuming that there is only one service provider, okay, it makes sense that this SP can freely choose P and RT. Of course, which ones will be those that maximize the profits. So this will be the usual way to proceed. Okay, there are more interesting scenarios, which are the following. That is, a scenario where there is more than one SP. Okay, those SP will be competing not only in providing service to the users, but also in getting sensing data rate from the sensor networks. Okay, let's get a little insight into this competition. Okay, at the procurement side, that is the competition between the buyers of sensing data that is supplied by the sensor networks, what we have here is a game. Okay, so it should be analyzed using game theory, and this simple game will be basically one simultaneous game where each player decides which amount R1, RE, RK will need for providing service to the users. Okay, and the total payoff will be minus the amount paid by each one of the SP. It is indeed a strategic game because the strategy chosen by an SP R1 affects the payoff of all the other service providers. Okay, how? Through the from the expression of the unit price that the inverse supply function gets. Okay. On the other side, well, just a comment regarding how can this be implemented. Okay. In this competition between the SPs when buying sensing data, we have seen that from the models shown before, each connected sensor network supplies a sensing rate Rj, and the total mean sensing rate has been computed as Rt. On the other side, each SP, each service provider, demands an amount Ri, and the aggregated demand is given by the sum of all capital K demands. Okay, so it is required that this total amount of sensing rate provided by the sensor networks is equal to the total amount of sensing rate demanded by the SP. Okay, however, a large amount of flexibility is needed in order to distribute this sensing rate in the specific quantities capital R, L to the different service provider. What I mean is that in order for this to be feasible, there is a need for a virtualization scheme implemented in the sensor networks so that the concrete and specific amount of sensing data rate that is needed by each one of the SPs can be delivered from the different sensor networks. Okay, although this point is not covered by our model. At the side of the service provision, we have another competition between the different service providers. Okay, each one of the service provider not only decides a price to be charged to the users, but also decides the total amount of sensing data rate to be used, because the amount of sensing rate is included in the user's utility. Okay, so it has an impact on the number of subscribers. Okay, so we have here again a non-comparative simultaneous game. Okay, although the strategy is both price and sensing data rate, and the payoff is the revenue that each SP ends up getting from its subscribers. Okay, of course these two games are played simultaneously, at least in this scenario, and the analysis should be focused on computing the Nash equilibrium. That is, a couple of values P R for each one of the capital K service provider, which are playing one against the other in these two sides of the market. Okay. Okay. We have computed analytically this Nash equilibrium, and as we may have guessed, the equilibrium is symmetric. Okay, since all the parameters are the same for each one of the service provider. I can provide you with the details of the analysis here. And I'm here just showing you a couple of results for specific values of the parameters capital N, which are the total number of networks present in the system, capital M, which are the total number of users, and capital K, which is the number of service providers. Okay, K is fixed to N, and M, capital N and capital M are changed in the different graphs. Here in these two graphs, I'm showing you the equilibrium price, okay, and the effect that the alpha parameter has. Remember that alpha measured the sensitivity of the users to the quality of service provided by each service provider. And what we see here is that as alpha increases from 1 up to 1.1, the price decreases, okay, for different values of M and for different values of N. That makes sense because if alpha increases, means that the users are more sensitive to the ratio R over P, so the competition between the service provider is stronger, and a stronger competition will translate into lower prices. Okay. We see that the effect of capital M is negligible, whereas the effect of capital N is more important. We see that as we increase N, the price charged by each one of the SP increases, which makes sense, since the greater capital N is, the more quality the service provider can deliver to the users, and therefore the price can be increased. As regards the sensing data rate, both from the networks, we see that apart from this specific case for M equal to 10, there is a very slow and negligible decrease in capital R as alpha increases. What we see is that as N increases, this equilibrium R increases, which makes sense again because we have a larger set of sensor networks delivering sensing data. Okay, and as capital M increases, there is only a slight increase in R. This curve, which corresponds to capital M equal to 10 and of course capital N equal to 10, is in the end not realistic at all, because that would mean that there is the same number of users than of networks, which is not a realistic scenario. We will always be looking at scenarios where there is an amount of users much greater than the number of sensing networks. Okay. In this work, as any analysis of a game, the existence of the Nash equilibrium should be proved, and we did it. I will not go into detail because I would like to spend more time in the second business model, but what we found is that, again, alpha, the parameter alpha, was the main parameter which with an influence to the very existence of the Nash equilibrium. Actually, in order for the Nash equilibrium to exist, alpha should be greater than or equal to 1. However, for values that are much greater than 1, Nash equilibrium will end up not occurring, which makes sense since higher values of alpha meant very sensitive users, and that meant stronger competition, which in the end will translate into a less stable strategic interaction, to give an intuitive explanation. Okay, so far an intermediation type business model for delivering service based on sensing data. I'm going to explain a more interesting, newer business model, which is called platform type. Well, this relates to the concept of two-sided markets, which you may have heard about. Basically, a two-sided market is more than just an intermediary-based market. In a two-sided market, there is an economic agent called platform, which creates value, allowing the direct interaction between two different user sets. Okay, so this facilitates the interaction between the different user sets. Okay, so it's not a true intermediary. Okay, it only facilitates the interaction between the two or more different customer sets. Okay, and the point is that in order for this platform to get positive profits, in order for this business model of a platform in a two-sided market be profitable, okay, there should exist a network effect between the different user sets, which is also known as cross-externality. One of the first examples where this two-sided market concept was applied is the credit card payment example, where the platform is the credit card platform. One user set are the credit card holders, and the other user set are the merchants. Okay, so the credit card platform enables the interaction between the credit card holders and the merchants, since this allows a transaction to be settled, okay? And there is indeed a cross externality between credit card holders and merchants, because the more customers get a credit card, the more useful this platform will be for the merchant, and the other way around. The more merchants subscribe for a POS terminal, the more useful a credit card will be for the credit card holders. So this cross externality, the more in this side, more satisfied the users at this side are, and vice versa, is the network benefits or the cross externality that the platforms take advantage of. Okay, so I'm here just presenting not a two-sided, but a three-sided platform business model within the context of sensor networks, within the context of Internet of Things. The problem with the services within the context of Internet of Things was that, I mean, of course, most players are no longer developing apps for their own sensing devices. To some extent, we can agree that this first phase is no longer the current phase, okay, since we are aware of platforms from APIs coordinated by Apple or Google that allows for different developers develop apps. Okay, the problem now is that main IoT-based apps are still integrating the apps and the sensor infrastructure. Okay, so a firm that builds AC-related sensor develops the app that processes this data and provides a useful service to the user. What I'm advocating here is that the platform, which might be Apple, Google, in the end, will be a three-sided platform between sensors, developers, and users. Okay, this will be an easy way to draw this scenario. Imagine that this IoT platform gathers data from different sensor networks, and this data is made available by the platform to the app developers, which are not required at all to own the sensing infrastructure. Okay, and these apps are made available to the users through the app. This interaction between user, platform, and developers is more common in the mobile application scenario. What is new here is that we add a third side so that there is a disintegration between the app and the sensor infrastructure. This will be the business model for one such IoT platform. Okay, that is a platform charging a fee to the users, a fee to the developers that wants to deliver apps to the users and wants to use data for their apps. Okay, and of course, paying a fee to the sensor networks. The sensor network will incur costs, which depend here on the upload requirements of each one of the sensors. And the developers get all revenues from advertising. Okay, while the users only pay for accessing the platform, not for each one of the specific apps. Okay. The IoT platform, as we will see later, will tune these three fees in order to take users, developers, and sensor networks on board. Okay. More specifically, this will be the specific expressions that we have used in this work for the utility of users, developers, and sensor networks. The simplest expression is the one for the sensor networks, which are paid an amount F, and they pay an amount to the access provider, which depends on their upload requirements. We have a utility for the developers, which is the profit, advertising revenue minus the fee paid to the platform. And this advertising revenue increases with the quality of the developer, QK, with the total number of sensor networks that connect to the platform, and increases with the total number of subscribers, since it is an advertising revenue. So it makes sense that it increases with M. Okay, and this alpha is a scalar. Okay, and the expression for the utility of the users is the following. This beta is a scalar. This omega is the willingness to pay of the user. Okay, so the difference between this and the price effectively paid gives a utility. So the greater his or her willingness to pay for a given price, the more satisfied the user will be. The utility increases with the total amount of sensing data that is used by the apps, and it increases also with the total number of registered developers in the platform. Okay, which makes sense, but it has been proved that in general, the app users are more satisfied as the more variety of application exists in a platform. Okay, so a couple of things. Okay, this dependence of the user's utility on the number of registered developers and on the number of connected networks, it is a cross externality from here to here and from here to here. And this is also a cross externality from the users to the developers and from the networks to the developers. There is no cross externality going into the networks. Okay, and this superscript E means that L is the number of registered developers that the user expects. Okay, and again, this alpha, which will be the most interesting parameter, can be interpreted, if we focus on here, can be interpreted as the value that the advertisers, that are the one paying the developers, attached to one user that subscribed. Okay, so the higher alpha is, the more valuable one user will be for the advertiser. Okay, in this model, we model heterogeneity using uniformly distributed random variables. Okay, the users are heterogeneous in their respective willingness to pay, omega. The developers are heterogeneous in their quality, and the networks are heterogeneous in their sensing rate. And from this point, we can compute the mean number of subscribers M, the mean number of registered developers L, and the mean number of connected networks N. Once we have those expressions, we can find for a given set of fees P, D, and F, we can obtain M, L, and N, assuming that all expectations from the different agents are fulfilled. That is, that the number of users that the developers expect that will subscribe will end up being the same as the mean number of subscribers we compute. And the same for the number of developers and for the number of sensor networks. Okay? The platform profit will be given by this expression, okay, the revenue from the users plus the revenue from the developers minus the cost incurred in paying to the sensor networks. And if we assume that there is only one platform, so we have a monopoly, okay, we can compute which fees P, D, and F will maximize this expression. Okay, we have solved this analytically, and we provide some results in this other paper, and I'm just giving you some simple results. Okay, I'm just showing you the profit maximizing fees, P, D, and F, and the mean number of subscribers, registered developers, and connected networks as function of alpha, which you might remember that it is the value that the advertisers attach to the users. Okay, and what we see here is the following. As alpha increases, that is, as the users are more valuable to the advertiser, the platform decreases the price charged to the users. Okay? Since they are more valuable and they will drive the registration of the developers, it may be profit maximizing to decrease the value, the price paid by the users in order to incentivize their subscription. Okay? Instead, the platform for more valuable users will be charging a higher fee to the developers, which obviously will drive some developers out of the platform. Okay? And eventually, for high enough valuable customers, okay, the platform may found profit maximizing to offer the service free to them so that all capital M users will subscribe. Okay? Of course, I mean, some registered developers should still be paying for the registration, okay? And what we see here is that if alpha is low enough, the profit maximizing fee choices for the platform will be the other one. That is, offering free registration to the developers, okay, so that all developers registered, and instead charging a non-zero price to the users, which end up in only having half of the total number of users subscribing to the service. Okay? This behavior of a trade-off in subsidizing one side of the other is quite common in platform business models. As regards the sensor network side, since there was no cross-externality playing at that side, we end up only having that as alpha increases, the platform chooses a higher fee to be paid to the sensor network, so the total number of networks will increase correspondingly. Okay? So, that's the other business model, which, as I have said before, is more interesting than just an intermediation type 1, although the computations are more complex, and therefore the model used here for the analysis is much simpler than the model we have been using for the intermediation type. And actually, this is just a model with one platform. So we have not made the analysis for different platforms competing one against the other yet, okay? But we plan to do so, okay? So these were the business model I wanted to show you, which just illustrate the sort of economic model that we analyze in order to prove whether a business model is sustainable or not, and which are the incentives of the different agents involved in the different business models. And what is interesting is that we borrow expressions for the utility of the different agents from our engineering background, which makes this research field, I mean, a bit different from the same type of analysis that economists make. Okay. These two examples are borrowed from these couple of papers, one published in JSAC and the other presented at the beginning of this month in one summer school held here in Paris, and I will be more than happy to provide you with this material if you are interested on. Thanks very much. Have any questions? I guess that nobody is working on economic modeling here. Is that right?
There are things which could be like related to blockchain that this thing could become useful for.
Yeah, I mean, I must confess that I heard about blockchain first time when I arrived here, and it's definitely very, very, very interesting from an economical point of view. Okay, of course, I mean, it is a different setting. Okay, but I mean, the economical incentives are that important in the distributed structures and protocols involved in blockchain that, I mean, if I end up, I mean, having a spare time, I will be familiarized with blockchain, definitely.
We can discuss it later. The question you mentioned that like you draw from the engineering background, like the constraints and the relationship between. But there are things like users, which like computer scientists model very badly actually. So how do you attach like utility, like in arbitrary cases, like for instance, number of applications, user happier, or like this kind of universals which are kind of, let's say, quite unfamiliar to computer scientists.
Well, I mean, this sort of, say, it's more than intuition. I mean, economists develop, publish, and analyze a large amount of field work based on questions and answers from real users. And I mean, that's the thing I find more useful from the economists' side, that they spend quite a lot of time just posting inquiries in the web, or just gathering all their students in order to get the opinion, and just doing econometric analysis and getting in this dependence. So this is the part I'm relying the most on economists' works.
Maybe a general question.
Yeah.
Regarding the coming IoT deployment, what are the, if you can cite some critical issues with business modeling for IoT in wireless communication? Are you, in case you are?
Well, I mean, actually, the main motivation of this work was the fact that, I mean, so far, platforms like App Store or Play Store allows you to download an app which takes advantage of sensing data, but the sensing infrastructure is owned by the same firm that is developing the app. Okay, so of course, the added value of the app is the sensing data that this app is using. So anyway, there are some research projects that are trying to, I'm not saying that the sensing infrastructure that a firm owns should be offered by free to any other app developers, but there are plenty sensor infrastructure. For example, sensing infrastructure owned by municipalities, or sensing data owned by weather station or water supply firms that can be exploited by app developers. Okay, so this might be a first step towards having these three sides clearly identified. And this might increase the take-up of this sort of apps, okay, as we may have seen in the mobile app arena. Apple gets most of its profits and added value, from the fact that the best developers decide to offer their apps through their platforms. Okay, so this might be one step forward. Okay, that firms owning sensing infrastructure have an incentive to offer the data to the platform, and the platform, of course, will offer them to developers, and those apps will be offered to the users.
Just a comment. There are already platforms on the IoT, like if this then that. Is one of the examples that for example, developers can create recipes with different sensors or different networks or different data coming from different providers, and offer these recipes for services to the users, and users use the platform to create. So you have. But there is no model, there is no economic modeling behind it.
Yeah.
It's like a service being provided. But it's interesting to see, see how this model can be
Yeah.
modified.
There
are real examples, and
yeah, I'm aware. And actually, I mean, you have seen that. I mean, even being this a business model, okay, when a platform comes into play, it may be in the interest of the platform or in the interest of all players that one side gets the service free. So I mean, even those experiences are in the sharing economy or in the open source or open data scenario. This may have a place here. Okay.
Thank you.
Thanks very much.